Okay. So, welcome again, everybody. And it's good to see a goodly number of people here. Our speaker tonight, I'm very pleased to welcome the new Professor of Astrophysics at Buist, joined Buist at the beginning of August, Roberto de Propris. Roberto did his BSc at King's College here in the UK. And for those of you who don't know, I'm Mike Bode. I'm speaking to you from the UK. I'm visiting Prof in Buist. And then he did an MSc, PhD at University of Victoria in Canada. Following that, he's been a NASA NSF fellow at Jet Propulsion Laboratory in Pasadena in California. Then swapped hemispheres to work in Australia at the University of New South Wales and the Australian National University before moving back to the UK on a fellowship at the University of Bristol, working with a group that I know pretty well down in Bristol. And then moving across hemispheres and again to work at the Charitalolo Inter-American Observatory in the Andes in Chile. Then just prior to coming to Buist, changed climatic conditions and hemisphere yet again to move north to Finland, to the University of Turkey, where he was a university research fellow. And then, as I say, we're very pleased to have welcomed him to Buist in the last few months. So, you can see the title of Roberto's talk is A Social Network of Quasars. We will, everybody apart from Roberto will mute their mics now, and I will then at the end we'll have time for some questions. So I'll hand over to you, Roberto. Thanks for doing the talk.
Part of this exposition we have been doing.
Roberto, sorry, Roberto, you're slightly, your sound is slightly poor at the moment.
Okay, can you hear me?
That's fine, yeah.
Yeah, okay, so this is essentially research that was carried out, well, it is being carried out actually, at the University of Turku, and it is actually part of this large survey called Gamma, the Galaxy Mass Assembly Survey, which has got the peculiarity of not being a very large survey like the Sloan or 2DF, but it is very complete. It tries to get everything. And so this survey is excellent for looking at the relationship between galaxies, and especially their environment. That is, whether the environment affects galaxies, or in this case, quasars. And essentially, you think like if you grow up in a bad neighborhood, like Liverpool, for instance, no offense intended.
No.
Then, of course, you probably won't turn up well. And I remember when I went to give a talk in Liverpool, once somebody told me, well, you have to be careful because if you're coming through Manchester and you park, you'll find your car on bricks unless you pay somebody with a baseball bat. And then you go to Liverpool and then you go to Manchester and they say, oh, you just going to Liverpool. Oh gosh, you got to pay somebody with a baseball bat or you'll find your car on bricks. Something like that. Anyway, so what is a quasar, by the way? Can you hear me, by the way?
Yeah,
Can you hear me?
Fine. Yeah, absolutely fine.
Yeah. So what is a quasar? Originally, actually, they will find there are bright radio sources in all sky surveys. And the first quasar was 3C295 from the 3C survey. It was identified as a radio source within a cluster of galaxies at a ratio of 0.46, which in 1960 was a completely unprecedented value. It was like at the edge of the known universe. And this image, you see, this quasar, you see it lives in a little cluster, and it is superposed with an X-ray image from Chandra, showing the bright emission from the quasar and the X-ray atmosphere of the cluster itself. So, and they were originally identified as radio stars. Once they had better radio interferometers, there were numerous identifications faint stars surrounded by slight nebulosities. And if you look at the figure, you see 3C48 in the upper right-hand corner, upper left-hand corner, and the upper right-hand corner. This is from HST. So you see there is a bright star and some fuzzy stuff around. And the same for the other two objects. Now, this is for HST. Consider doing it from photographic plates back in the 1960s, in the bad old days. And you see they were often used just to a bright star. But like all the other stars in the sky, you were emitting in the radio. And the spectra of these objects, when they were taken, showed very unusual broad emission lines at unusual wavelengths. And so they were essentially unknown objects. Somebody even thought they were made of elements which didn't exist on Earth, as a matter of fact, because people couldn't identify the wavelengths. A precise position for an object was determined for 3C273, and it was done via lunar occultation. And these were again identified with a bright star with unusual spectral features similar to those found in 3C48. And for the first time, you saw that there was a little jet coming out of the star. And the spectrum was finally identified by Schmidt, who died recently, by the way. And this was identified as belonging to hydrogen, redshifted ratio of 0.16. And this proved that, once and for all, quasars were actually objects lying at large distances, and were bright stars, bright nuclei of galaxies. The small scales, of course, even at the resolution available from photographic plates, it was clear that the size of quasars were very small, of the order of half an arcsecond, and that they were variable over scales of the order of a few days, which indicated that the sources were actually small. They couldn't be bigger than a few light days. And so once it became clear that the quasars lie at cosmologically significant redshifts, the question then shifted to the nature of the energy source. The diversity of the antinuclei, of which there are very, very many, like quasars and radio galaxies and Cephers, and why do you find a quasar in some galaxies but not others? And it soon became clear that the luminosities of these objects were comparable to those of entire galaxies and were produced within regions of the size of a few tenths of parsecs, if not less. And actually, in 1969, it was Lyndon Bell, as a matter of fact, the famous British theorist that argued for a paradigm in terms of an accretion disk around supermassive black holes. And through essentially a few tens of years of research, it became clear that the paradigm was essentially correct, that the quasars are essentially accreting supermassive black holes of the order of several million to several billion solar masses. And so unification model, AGS is called the unification model. So what you see is a supermassive black hole in the center. It is surrounded by an accretion disk of matter. And because you have to get rid of the angular momentum, jets emerge from the disk perpendicular to the disk. And the whole must be surrounded by clumpy torus of gas and dust. And it turns out in this model that all the types of quasars we know, from quasars to blazars to Cepher galaxies, are actually the same kind of object observed at a different angle. Indeed, the unification model looks something like this. So the quasar, the black hole is the center with the accretion disk, and around it is the dusty torus. So if you're looking straight down the jet, you're essentially looking at the relativistically accelerated particles, because the jet is essentially moving at velocities close to the speed of light. And what you're seeing is a very flat, very blue source. And what you're seeing is a blazar of BLAC or of FCRQ. If you're looking at a slightly different angle, then you don't look just in the jet, but you're looking at the clouds of dust, clouds of gas around the quasar, which are narrow line and broad line regions. And so you look at the type 1 quasar or the broad line radio galaxies. And if you were to look really almost down the torus, what you see is a radio galaxy or a narrow line radio galaxies or a Seyfert galaxies. So in reality, all the quasars are essentially the same kind of object, but observed at different angles. And then the question is, why do galaxies have active nuclei and others do not? And one of the most likely hypotheses is that you need some way to trade the gas and dust to the black hole and feed it. But it is very hard to do so. You need to lose a lot of angular momentum. So you need to torque the galaxy and the gas and the dust in. So in order to do that, you need something violent. And usually a good violent way is mergers and interactions. Mergers and interactions relax the gas and they allow it to flow to the center, where the quasar can start to accrete. And so the model essentially that you start with an isolated galaxy, down in the bottom left corner, and it's behaving normally. It may accrete companions. Eventually, it starts to interact with a companion. At this point, you start forming stars, and then the two galaxies merge. And at this point, there is enough gas to quasar. At the beginning, the quasar is by dust. You can only see the X-rays, but eventually it blows out the gas with dust. You start to see the bright quasar.
Roberto, your sound is slightly muffled again. Sorry.
Now it's better, right?
Yeah.
So the quasar essentially blows out the gas. At this point, you see a classical quasar. And then the quasar essentially dies because it is no longer being fed. There is no more gas, or because it manages to eject all the remaining gas and dust, either because of the ultraviolet light or because the mechanical energy into. At this point, the quasar fades rapidly, and all you see is a messy galaxy, which then settles into what looks like a dead elliptical or lenticular. So the idea is that quasars are a way to transform galaxies from star forming to non-star forming, and from spiral to ellipticals via mergers. And this is important because if there were no quasars, if you didn't manage to stem the star formation, you see a lot of bright blue ellipticals, which is never seen in the universe. On the other hand, it is perfectly possible to actually feed quasar via instabilities in disks, such as the formation of stellar bars. And now we know that this has been done from Hubble Space Telescope. And if you look at normal galaxies at the same redshift and active nuclei, you find that there is no significant degree of difference in morphological disturbance between these two objects, which argues against mergers being important. So our approach is essentially to say this. Let us look at the environment of the quasar host galaxies, understand the nature of their neighbors, and look at their stellar populations. And then we'll compare to the normal or the inactive objects at the same stellar mass and the same redshift. And that will tell us whether mergers are important or whether quasars are essentially accidents that happen to every galaxy. And from this, we use the Galaxy Mass Assembly Survey. And this is essentially the usual redshift position plot. While Sloan and 2DF are very broad, but they're not relatively shallow. Gamma is also smaller, but it goes considerably deeper and is much more complete. However, this means, of course, you only look at a small section of the sky. 3 equatorial patches and 2 in the southern hemisphere. And so our standard procedure is this. We look at known associated criminals or crime victims. And then we try and figure out, well, what's wrong with this person? Because, the first person they look, if you are a victim of a crime, is your friends. They're most likely people that are going to commit crimes. And so what we need is a comparison sample of honest or non-active galaxies to compare with. And Gamma offers it to us because it has got 200,000 galaxies, and we can find galaxies which are inactive, but are the same properties as the quasar host galaxies. in order to avoid biases, we actually select quasars from a different survey, which is a large quasar astrometric catalog. And what this is a survey that just identifies quasars independently of gamma. So we know that the two surveys got nothing to do with each other, and therefore we're not inducing any bias between the two selection samples. And then the comparison sample of galaxies come from gamma. So LQAC4 is actually a compilation of all available quasar catalogs. So it is most complete sample of quasars, while gamma is the most complete survey, which photometry in 22 bands and the set of dry quantities. So the two things complement each other very well. So the first thing is we match the quasars to gamma sources within the redshift range where gamma is most complete, and we require the objects to be within 3 arc lengths of each other, which therefore means they're probably the same object. And then we drew 100 comparable samples of non-active galaxies, but having the same mass and redshift as the quasars. And you can see that the samples are perfectly matched to stellar mass. A stellar mass is probably the most important thing that determines what a galaxy looks like. So the first thing we did, we plot the average number of neighbors, which are within 100 kiloparsec and with a velocity difference of 1,000 kilometers per second of gamma quasars. And then we compare to the distribution of average neighbor counts for the 100 realization of the matched galaxy sample. So essentially, we do a Monte Carlo simulation of the quasar host galaxies. And what we find is that there is no statistical difference between the local environment of the quasars and the inactive galaxies. And this indicates that the environmental dependence is weak. Now, if there were a lot of mergers, we would expect quasars to be strongly dependent on their environment. They will need more companions, but we don't see anything like that. So this favors a model where secular processes are responsible for quasars. We then looked at the group environments. So most galaxies live in small groups. Our galaxy lives in a group with M31 and M33 and the Magellanic Clouds. So it's a small group with 2 large galaxies and 3 sort of middling galaxies and a lot of little dwarfs. So groups are the typical place where you find galaxies. So we compared the fraction of galaxies in groups, and then we compared the fraction of group galaxies between our matched galaxy samples, where the shaded region denote the uncertainties. And so what we find is that the likelihood for a given galaxy to exist in a group is not affected by the presence of a quasar. So there is no statistical difference in the group environment of quasars and the inactive galaxies at low redshift. And in addition, we find that the groups containing quasars have the same multiplicity as the groups that do not contain quasars. So there is no difference in the typical group size of either population. So the quasars seem to live in galaxies which are perfectly normal. However, the interesting thing, and that's the one interesting thing we found, actually, the one interesting difference we found is that quasars really like to be the central galaxy in a group if they lie in a group. So there is something about being the main galaxy in a group that makes a quasar more likely, but not anything else. Then we looked at these other indicators of environment. We looked at the surface density of galaxies, the sigma phi, which is the moving distance in megaparsec to the 5th nearest neighbor, d5 within 1,000 kilometers per second, accounting a cylinder around galaxies, which lie within a radius, with a cylinder radius 1 moving megaparsec, and then the distance to the 5th nearest neighbor, measured in units of megaparsec, across the gamma sample and the matched sample. And what we find is, again, the insights show the Cosmogorov-Smirnov test, that there is no real difference between the two environments. So quasars and galaxies live in the same broad environment in terms of density. There is another way of characterizing environments, and essentially galaxies can live in a void, which is a region almost devoid of galaxies. They can live in a filament, they can live in a wall, and they can live in a knot. And a knot is essentially a cluster. And so these are 4 different environments with different densities. Voids are very underdense, knots are very overdense. And so we check that whether there is the fraction of quasars in gamma existing in each environment, void, sheet, flatman, not, based on the on a geological classifier. And again, we compare to our inactive galaxies. And in this case, we have to look at a slightly lower redshift because gamma doesn't have the environment for the more distant object. There are just not enough galaxies to compute the environments. And what we find again, that in terms of large scale structure of the universe, the quasars do not care. They live exactly the same environment as all the other galaxies in the universe. So this means essentially there is nothing special about being a quasar. But that means, of course, this is very unlikely. This makes it very likely that mergers are important. And then we look at star formation, and this is the surprising thing. In reality, most of the quasar-host galaxies lie on or above the main sequence of star formation for normal galaxies. Very few lie in between, and almost none in the amorphous area of quiescent objects at the bottom of the plot. This tells you that quasars do not quench galaxies. In reality, they're associated with more star formation. We do find, indeed, that if you plot the fraction of galaxies and the specific star formation rate, what you find is that the quasars lie in the same little peak as normal galaxies, but the peak is broader and the star formation rates are higher. So quasars are indeed associated with higher star formation rates, not with quenching. And indeed, we find actually that this is true over scales of 100 million years and 20 million years, but not over 1 billion years or 2 billion years. And this essentially means that quasars are correlated with a recent increase in star formation. So in reality, it is the opposite thing. Star formation starts, feeds the quasar, and the quasar then dies as soon as the star formation is quenched. But the quasar itself is not quenching the stars. So we conclude that there is no strong evidence the quasars lie in any particularly dense environment. This suggests that external events are not necessary. And also there is no evidence for the quenching model that I was showing earlier. Essentially, this model here, if you remember, essentially, we don't see any of this. We don't see any evidence of this quenching. Let me go back. So it appears, therefore, that in reality, you first forming stars again, and this increases AGN activity. And once it quenches on its own, the AGN activity stops. So this famous relation between the small of this black hole, the mass of the black holes, and the bulge and the mass of the galaxy is actually not due to causal events. It's a causal event due to essentially to the central limit theorem. I guess that's it. Hello?
Okay. Oh, thank you, Roberto. And I'll open it up to questions. So either raise the hand or just speak up, and if anybody wants to ask a question of Roberto. Roberto, I just wonder what's the next step in all of this? Is this?
Well, we're actually doing two things. We're essentially doing three papers. The first paper is actually this one on the star formation, which we are going to write up. The second paper we are doing is a paper on whether quasars affect their neighbors. In other words, if you look at the neighbors, is there any difference between the neighbors of quasar and the neighbors of the non-quasars, if you wish? And then the third thing we want to do is to look at the morphologies of the quasar-host galaxies, which is hard because, of course, there is this bright quasar in the middle. So we're going to try it from the ground with the imaging we got from Sloan and from the Viking survey. But we're also applying for this. There's a thing on HST where you can apply for sort of spare time. And we are going to apply those for them to look at a small sample of these objects, as many as we can get, so that we can look at the morphology without this bright quasar interfering with us. Because the point spread function is going to be much smaller.
Okay.
And then, of course, it would be nice to do integral field units and do the spectroscopy. Yeah. So really figure out what's happening to the star formation really close into the quasar.
Okay, thank you. We have other questions? No? Gian, yeah.
Yes. Roberto, why is it that the Milky Way galaxy doesn't have its own quasar?
Quasar. Well, it does, but essentially it's not eating at the moment. I mean, it's a supermassive black hole, and it even burps something up because there are these two large Fermi bubbles, which have recently been discovered, but clearly doesn't have a high accretion rate at the moment.
Mm.
But it did eat something fairly recently, because if there are these two really big Fermi bubbles of hot gas, which has been ejected from the AGN relatively recently. So it did consume something, it was just not very big. It's actually good news because it will flood the UV, it will flood the Milky Way with UV radiation, by the way, which is not good.
Okay. Okay.
Okay, thanks again. Any other questions? I'm just looking to see if there are hands raised. Alistair?
Thank you, and thank you for that talk, Roberto. Of course, your conclusions have words like suggest and appears that and so on. How confident are you of all these results? Do you think that they will bear out in further investigation, or could you feel there might be changes to these conclusions?
Well, the thing is, essentially, this is a sample of relatively low luminosity quasars by selection, because we're looking at quasars in no particular area. They just have to be within a given volume, and most of them will be low luminosity quasars. So the question is whether the high luminosity quasars behave the same way. And then the question will be, okay, this is true at low redshift, which is the local universe. We're essentially looking at no more than 2 billion years in the past. But the peak of quasar activity in the universe is at a redshift of 2, which is essentially at around 8 billion years ago, 8 billion years in the past. So the question would be, is it the same high redshift and for high luminosity quasars? Because it is perfectly possible that at low redshift like now, maybe most of the interesting stuff in the universe is gone, mergers are starting to wind down. So what's left is one particular channel of quasar formation. But when the universe is younger and quasars are more active, maybe there is a different quasar formation mechanism. So essentially, we need to both go to brighter objects and to higher redshift.
Right, I see. Thank you very much.
Okay. Thanks, Alistair. Any other questions from anybody? Okay. If not, I'd like to thank Roberto again for a very interesting talk, and we'll watch this space for future developments, and be particularly interested to see how the group as a whole develops at BUST under Roberto's leadership over the next few years. And thanks again to everybody. I don't think there will be a talk next month because it's Christmas, isn't it? So I guess the next talk to the Society will be towards the end of January. Is that correct, Ian?
That's right. That's correct.
Okay. So hope to see everybody then. And so have a happy Christmas, as Harold said earlier on. And we will see everybody in the new year, if not before. So thanks again to Roberto. Thanks everybody. For those people on the committee, there was a committee meeting immediately after this. So I'll see the committee there. Thank you.
Thank you very much.
Thank you.
Thanks a lot.
Thank you all. Good night.
Good night.